Welcome back. The topic for our videos today is factors of safety and reliability. The traditional way we calculate factor of safety using a limit equilibrium slope stability method is to take the shear strength of the soil, the forces resisting failure, divided by the shear stress required for equilibrium, or in other words, the forces working to resist failure, and that gives us our factor of safety. Factor of safety less than 1 means that the slope would likely fail. If it's greater than 1, it means it is likely to be stable. However, what does that mean in practice? I mean, suppose you have to make decisions regarding safety. Maybe some lives are at stake if the slope fails. So what does a factor of safety, for example, of 1.3 mean? Is that going to be good enough? And what is a proper factor of safety given the circumstances surrounding a project, and what is the difference between a factor of safety of 1.3 and 1.5 when it comes time to make decisions? A lot of these construction projects, the factor of safety you choose will impact literally millions and millions of dollars. What do we do with that? Well, there are some guidelines on factors of safety to use. And this chart is from the U.S. Army Corps of Engineers Slope Stability Method. Up at the top, there are guidelines regarding a range of factor of safety to use in a number of different circumstances. The first line is the cost of repair is comparable to the cost of building a more conservative slope. Meaning, if it fails, it'll be expensive, but maybe not catastrophic. And if you have, then the factor of safety you could consider would be between 1.25 and 1.5, depending on how certain you are about the analysis conditions. And that would mean the layering of the soil, and the material properties, the strength parameters. How many samples have you taken? How confident are you in that? If you don't have a lot of data to work with, maybe you'd go with a higher factor of safety. But if you're pretty sure about the quality of your data, you could get by with a lower factor of safety. Now, there are circumstances where the cost of repair is much greater than the cost of building a more conservative slope. For example, if you had a dam or a levee, if it broke, it would potentially do massive amounts of damage. Therefore, you're going to want to use a higher range for your factors of safety. And then the Corps of Engineers, they're involved with a lot of dams and levees. And so they also, for a given project, there are different kinds of different scenarios that you run. For example, for a dam or levee, they do an end of construction slope stability analysis where you use undrained strength, unconsolidated undrained strength parameters. And then for long-term steady-state seepage, you do an effective stress analysis with the pore pressures with a piezometric line, where the pore pressure is drawn from a seepage finite element program. And then you'd also consider rapid drawdown. Some point, after a long time after the reservoirs come to equilibrium, you get a rapid drawdown case. And end of construction. Now, why do these vary? End of construction 1.3. That's a relatively short period. If it fails, then maybe the reservoir is not likely to be full, but it's over a shorter period. Long-term steady-state seepage, that is the longest term and most likely condition, and so you want to be a little more careful there. Rapid drawdown, you could get away with a lower factor of safety because it's less likely to occur, and if it does, it's most likely to result in a failure on the upstream side, and maybe it wouldn't represent a complete collapse of the dam. So those kinds of considerations come into effect here. But still, there is a different way to look at slope failure. So instead of using a factor of safety, we can look at reliability and probability of failure. And so the probability of failure would be, what is the percent likelihood that a dam or a slope is going to fail? Is it 10%, 5%, 1%? That's a pretty intuitive thing. The reliability is 1 minus the probability of failure. So if you had a 5% probability of failure, that means the reliability would be 95%. So both of these terms are numbers can be far more useful than a factor of safety when we're making decisions about risk and about how much, how to spend our money. Should we spend another $1 million and make build a more mild slope? And what would that do to the probability? And it's just a more rational way of assessing risk and making these kinds of really important decisions. So how do we go about doing that? That's the purpose of these videos, is to describe how you would go about calculating a probability of failure and a reliability for a slope using a slope stability analysis. So in order to do this, we start out by assessing the uncertainty in each of the input parameters. How much variation is there in our shear strength, for example? The primary uncertainty relates to shear strength because it has the most variability, but there may also be a range of uncertainty in other parameters. Unit weight is pretty straightforward and easy to measure. There's some uncertainty in the pore pressure. You've seen that our analyses are dependent on hydraulic conductivity, which can be a little tricky to measure. But there's a lot more spread or scatter or deviation in the undrained in the strength parameters, both drained and undrained. And that uncertainty is typically represented using some statistical measures, principally the standard deviation or the coefficient of variation. If you've taken any kind of statistics, you know this is how the standard deviation is calculated. It's it's one of the most primary things we do with data, is calculate the mean and the standard deviation. The mean is the average value. The standard deviation is how much a typical sample varies from the mean. And so it's a measure of how much spread or scatter you have in your data. A small standard deviation means most of the values are the same. A large standard deviation means there's a lot of variation in your input, in your parameter value. And the coefficient of variation is the standard deviation divided by the average value. And what that does is it normalizes the standard deviation, and it puts it in terms of a percentage. So, for example, a coefficient of variation of 0.23 or 23% means that on average, the values, the sample values, deviate from the mean by a magnitude of about 23%. And so it's a pretty intuitive and useful measure of the standard deviation. And in our in-class exercise, we're going to go through some calculations that how to go about computing the coefficient of variation and the standard deviation. So if this is a frequency histogram, this is one that I put together. I have some code where I can give it a mean and a standard deviation and tell it how many samples I want, and it'll artificially generate samples that are either normally distributed or not log normally distributed. These are normally distributed, so assume that 400 is your average undrained strength. That's a fairly typical value. And that the standard deviation is 100 PSF. If you generate 200 synthetic undrained strength values and then plot a frequency histogram, in this particular instance it looks like this. Now if I ran it multiple times it would look a little bit different, but basically what you're seeing here is, is that classic bell shape showing what we call a normal distribution. Now, in this case, I'm using a mean and a standard deviation to artificially generate values, but what we need to do is the other way around. We need to take sample values and from that calculate or estimate the mean and the standard deviation. So, in order to do that, you have to have a lot of samples. But if you have a lot of samples, of course, it's just a very trivial spreadsheet calculation. The problem is we rarely have enough samples that we can directly calculate the mean and standard deviation, especially the standard deviation, and have a lot of confidence that that's a representative value. Therefore, what do? We need this. We need to know what the standard deviation is in order to do an uncertainty analysis, calculate our probability of failure and reliability. So how do we come up with that? It turns out there are some pretty effective and useful ways to infer these values, and we'll talk about that in these slides. So the one that we primarily use is called the 3 sigma rule, the 3 standard deviation rule, and that is it can be shown that 99.7% of all values will fall within plus or minus 3 standard deviations. In fact, if something's outside that range, you call it an outlier. And so if you can estimate what the max and min expected values are, then you can back calculate or estimate the standard deviation by taking the max minus the min divided by 6, because you have 3 standard deviations on each side of the mean. And so over the range between the min and the max, you'd have 6 standard deviations. However, studies have shown that even experts often underestimate the spread between the max and the min values. Therefore, if you want to be conservative, you can estimate the standard deviation as the max minus the min divided by 4. In other words, you using your judgment and looking at the data you have, you come up with a maximum expected value and a minimum expected value and divide that by either 6 or 4. And again, we'll do that, go through that process in our in-class exercise. If you have data that can be plotted on a graph, you can use a graphical method. So this is undrained strength versus depth, and they're plotted out, and then somebody looks at this and then plots this dashed line representing the highest conceivable value and then the lowest conceivable value. And then you calculate the average would be halfway between that, and then you go about 1/3 of this span on each side and you have 1 standard deviation. And in this case it varies versus depth, so that's but you could get from this a C over P ratio, which is basically the slope of that line corresponding to the mean and plus or minus 1 standard deviation. Here's another example. We have some more circles from say triaxial shear tests. Assuming that there's no cohesion, you could calculate, draw a line to calculate the average friction angle. And then if you were able to draw a lower line and an upper line representing your highest conceivable and lowest conceivable value, and then divide that span on each side into a range of about 3, and go 1/3 of the way to the high side and 1/3 of the way to the low side, and there you have your plus or minus 1 standard deviation. Scale off the angle corresponding to those, and you're good to go. And so using this method, there have been a lot of published values on the coefficient of variation in terms as a percentage. Again, that's the standard deviation divided by the mean value. And it's kind of interesting to look at. Again, unit weight, Boyett unit weight, those have a pretty small coefficient of variation. We can get those fairly accurately. Effective stress friction angle is not too big. Undrained shear strength, and that there we have a much higher spread. Standard penetration blow count, that's related to the undrained shear strength. It's in the same range. And there's a number of different ways in calculating the undrained strength with different tests. And so these are fairly typical ranges that we're looking at for the coefficient of variation. So again, so we do have a way of rationally assessing or estimating the coefficient of variation and the standard deviation. And then, of course, you can always compare the values you've come up with tables like this and published values, and get a pretty good feel for what a reasonable value is for different kinds of material properties that go into a slope stability analysis.